Hey everybody, I'm Silas, and welcome to Psilocybology. Let's expand our mind. This is a series where we talk about the research on psilocybin, the psychedelic prodrug found in magic mushrooms. If you'd like to support the show, please rate, review, and subscribe to the podcast wherever you can. And be sure to share the podcast with anyone you know who might enjoy the content. For the month of January, you can also support the show by participating in the biannual listener survey, where you can provide invaluable feedback about the podcast. The link to the survey can be found on the front page of the website, psilocybology.org. As always, thank you for your support. Today's episode is on the article titled Interrelations of the Effects of Psilocybin on Subjective Sensation, Photopic Critical Frequency of Fusion, and Circulating Non-Esterified Fatty Acids, published in 1963. It's only a 2-page article, but it's pretty dense, so we should have plenty of content to discuss. Let's start by just going through the title and defining what exactly the author of the study examined. Photopic vision refers to our vision under well-lit conditions, and our eye's ability for color perception. It is often contrasted with scotopic, which is our vision under low-light conditions. Critical frequency of fusion is the frequency or rate at which an intermittent light stimulus, such as a flickering light, appears to be constant and unchanging. It is also sometimes called the flicker fusion threshold or the critical flicker fusion frequency. It might help to think about frame rate as an example of what this means. When you're watching a movie, even though it is just a series of still images called frames appearing in rapid succession, because the frame rate is so high, they appear to fuse together to produce one continuous motion film. In this study, the critical frequency of fusion is defined as, quote, the minimal rate at which intermittent photic stimuli are perceived as continuous illuminations. The reason the study author decided to examine photopic critical frequency of fusion, or CFF for short, is because an earlier study found that LSD significantly increased CFF. This meant that after being given LSD, an individual would require an intermittent light source to flicker at a faster rate in order for it to appear as a continuous stimulus, compared to when they were not on LSD. Since psilocybin also produces changes to visual perception that are similar to LSD, the author wanted to see if this drug also increases the CFF of participants. The other primary outcome of the study is circulating non-esterified fatty acids, also known as free fatty acids. The circulation of fatty acids comes from the breakdown of triglycerides, which are the main constituents of body fat. In last week's episode, we mentioned how chronically elevated levels of free fatty acids are often found in obese individuals, and that they have been linked to increased insulin resistance and appear to activate some inflammatory processes. What's important to understand about the health implications of elevated circulating fatty acids, however, is the metabolic context. The cells of individuals with diabetes, for example, have an inability to take up glucose and use glucose as a source of fuel. This inability results in a greater demand for fats as a fuel source. The elevated circulating free fatty acids can be seen as a product of a dysfunction in how insulin works in individuals with diabetes, which then also unfortunately produces further health complications. This is very different than some of the other factors that can cause acute elevations in free fatty acids, such as an increase in catecholamines. Catecholamines include the organic compounds epinephrine, also known as adrenaline, norepinephrine, and dopamine. Taking a bit of a step back, this is actually why the author chose to measure circulating free fatty acids. The intent was to have an indirect measure of assessing changes in circulating epinephrine and norepinephrine after psilocybin administration. As we discussed in prior episodes, and as many of you might be aware, psilocybin stimulates the sympathetic nervous system, which is part of our autonomic nervous system responsible for the flight or fight response. Excitation of the sympathetic nervous system leads to an increase in the adrenergic agonists, epinephrine, and norepinephrine. The reason the author chose not to examine circulating epinephrine and norepinephrine is because to do so, at least at that time, was, quote, technically difficult and requires relatively large amounts of blood, a problem if serial determinations are necessary. As we'll see in a bit, this study took a series of measurements over a relatively short period of time, because the aim was to investigate the temporal relationship between all of the outcomes of interest, and needed to get fairly precise measurements of when exactly changes started to occur after psilocybin administration. So overall, because sympathetic stimulation produces relatively rapid and acute elevations in free fatty acids, and at the time other factors that induce elevated free fatty acids were known to take hours or days to exert their effects, the author felt confident that any short-term elevations in free fatty acids could be used as a proxy measure of elevated levels of epinephrine and norepinephrine. One last thing I want to note about free fatty acids before moving on is that another known cause of elevated free fatty acids is fasting, because during periods of fasting, fat becomes a more important fuel source. As you might recall from previous episodes, many studies into psilocybin administer the drug after a period of fasting for about 8 to 12 hours. In order to make sure that the elevated free fatty acids were not simply a result of fasting, the author did 2 additional critical tests. First, they conducted preliminary studies that found psilocybin produced increases in free fatty acids in non-fasting subjects as well as fasting subjects. Second, they compared psilocybin to a placebo administered to individuals who had undergone the typical fasting period, and found that the placebo did not cause elevations in free fatty acids. Now that we've covered the measures in hopefully sufficient detail, let's finish discussing the rest of the design and methodology for the study. As I briefly alluded to earlier, the goal of the study wasn't simply to measure if and how psilocybin produces changes in CFF and free fatty acids. Rather, the aim was to focus in on the time course of any such changes in order to see how these 2 outcomes were interrelated and how they influence the subjective experience of psilocybin. The author notes in the introduction that even if psilocybin produces subjective changes to visual perception and also produce changes in CFF, this doesn't tell us whether or not these phenomena are caused by a shared biological pathway. It's possible that they are in fact both reflections of a similar underlying physiological process, but it is also possible that they are reflections of 2 separate physiological processes that just both happen to be influenced by psilocybin. The same could also be said with the relationship between subjective experiences of psilocybin and free fatty acids, which again we're using as a proxy for epinephrine and norepinephrine. One way to establish evidence supporting the notion that these effects do depend on a common process is to determine if they are temporally coincident, or in other words, if they occur around the same time after psilocybin administration. This doesn't prove anything conclusively, but it does lend support to their interrelatability. So, to assess temporality, the author measured subjective experience, CFF, and free fatty acids just before administration and every 30 minutes post-administration for up to 4 hours. We haven't discussed this yet, but to measure subjective experience, the author used a 76-item checklist that had previously been developed to identify and distinguish a psychoactive drug from a placebo. Although the sample size for this study is incredibly small, which is probably why this is a brief report rather than a lengthier manuscript, what they found was interesting and, if nothing else, thought-provoking. In total, there were 7 participants. 5 were given a dose of 14 milligrams of psilocybin per 70 kilograms of body weight, or about 154 pounds. The remaining 2 were given a dose of 3.5 milligrams per 70 kilograms body weight. The rationale for the latter and smaller dose was to determine if changes in either CFF or circulating free fatty acids could be produced without the presence of any subjective effects of psilocybin. Although they wouldn't have used this term here, this is in essence an early example of investigating the mechanisms of microdosing. For those who might not be familiar, the idea for microdosing is to take a very small amount of a drug and often today we hear about it with psilocybin or LSD, that would be too low of a dose to produce perceptible psychological effects, but just high enough to produce some effects at the cellular level. In this case, the author wanted to determine if, potentially, CFF or circulating free fatty acids might be two such effects that are produced even when only given a low dose of psilocybin. The results were presented as the time in hours after drug administration it took to see either a, quote, definite or, quote, marked increase in subjective experience, CFF, or circulating free fatty acids. Compared to baseline measures, a definite increase was defined as at least 6 more positive questionnaire responses, an increase of at least 1.5 flashes per second in CFF, and an increase in at least 100% of the circulating free fatty acids. A marked increase, again compared to baseline measures, was defined as at least 14 more positive questionnaire responses, an increase of at least 3 flashes per second in CFF, and an increase of at least 200% of the circulating free fatty acids. Starting with the participants who received the 14 mg per 70 kg body weight dose, all participants showed at least a definite increase in questionnaire responses starting at about 30 minutes, which lasted between 3 to 4 hours after administration. Participants showed a marked increase in questionnaire responses starting about 1 hour after administration and lasting till about 2 to 2.5 hours after administration. To restate that, there was a definite increase after 30 minutes, which became a marked increase after about 1 hour, and then returned to just a definite increase 2 hours after administration, and returned to baseline 3 or 4 hours after administration. For CFF, all 5 participants showed a definite increase between 30 minutes and 1.5 hours after administration, reaching a marked increase between 1 to 2 hours. The marked increase lasted until 3 to 4 hours after administration, so it appeared that although the onset of subjective experiences and the increased CFF were similar, the marked elevation in CFF had a longer duration than the marked increase in subjective experience. For circulating free fatty acids, only 4 of the 5 respondents showed elevated levels after psilocybin administration, and in 1 of those 4, the effects were substantially delayed, where elevations were only seen 2.5 hours after administration, despite the subjective effects for that individual being present 30 minutes after administration. The remaining 3 participants all experienced rises in free fatty acids that mirrored the increase in CFF, with definite increases appearing after about an hour and marked increases appearing after 1.5 hours. The author notes that this finding shows us that the subjective experience of psilocybin is not dependent on a simultaneous increase in circulating epinephrine or norepinephrine. Importantly, they add that this does not mean that epinephrine and norepinephrine don't contribute to part of the effects of psilocybin, just that epinephrine and norepinephrine are not necessary or sufficient causes of the psilocybin experience. I think a follow-up study to confirm this would be interesting, possibly by using drugs like beta blockers, which act as competitive antagonists for epinephrine and norepinephrine. It would also be valuable to confirm that circulating free fatty acids is an accurate proxy measure for these catecholamines. Finally, for the 2 participants given the 3.5 mg per 70 kg dose, they found that the only positive result was a definite increase in CFF for 1 of the 2 participants that started 1 hour after administration and ended 2 hours after administration. This low dose appeared to have no other effect on the outcomes assessed. Although this doesn't provide much help elucidating some of the mechanisms involved in microdosing, it does at least make the case that it's possible to detect some physiological changes in response to psilocybin in the absence of any subjective effects of the drug. I do want to qualify this finding specifically, however, by noting that the authors do mention that this increase in CFF may have been caused simply by anxiety on behalf of the participant, as anxiety has been shown to increase CFF. Since there were only 2 participants given this dose, there really is no way to tell. I definitely wouldn't use this to make any claim that low doses of psilocybin increases CFF, Rather, I would use this more as a thought experiment and an example of how one could study microdosing. Well, that's it for today's episode. As always, I really hope you enjoyed the show. If you have any questions, feedback, or ideas for the podcast, please let me know. You can find out all of the ways to reach me on the website, psilocybology.org, where you can also find the full transcript for each episode if interested. Thank you all for listening, and I'll talk to you next time.